The equal sign is a precise mathematical symbol that requires significant effort to ensure both sides are balanced. For example, calculating e to the power of 0.1 without knowing the formula or using a calculator or programming would be challenging. An even more challenging question is what does e to the x equal when x being any real number? We know that we can find the value of e to the x at a specific point like x equals 0. To approximate e to the x at x equals 0, we can use any function that equals 1 at that point, such as this function. Can we do better? Can we find an equation that is close to e to the x, at least in the neighborhood of x equals 0? The issue with this approximation is that in the neighborhood of x equals 0, its rate of change, or slope, differs from that of e to the x. The requirement for the approximation to be accurate near x equals 0 is that its derivative at x equals 0 matches that of e to the x. We can revise our approximation accordingly, giving us y equals x plus 1. This ensures two things. First, the values are the same at x equals 0. Second, the derivatives are the same at x equals 0. Our approximation is still insufficient because the original function is a curve while our approximation is a straight line. Can we do better? The key issue with our approximation is that its slope is constant while the slope of e to the x varies. In other words, the rate of change of the slopes are different. Since the rate of change of the slope is given by the second derivative, we can improve our approximation by adding a third condition. The second derivatives are the same at x equals 0. To further improve our approximation, we could continue adding conditions for the third derivative, fourth derivative, and so on. While we have the idea, how can we achieve this? To satisfy conditions for the third and fourth derivatives, our solution should probably include terms up to the third and fourth powers of x. Without technology, we can try this approximation and compare the graphs. It seems to be better, which suggests that adding higher power of x could improve our approximation. What about this approximation? Although the fit in the right neighborhood is worse than before, the improvement in the left neighborhood outweighs it. It seems that adding higher order terms of x might improve the approximation. We might never achieve exactly equal. Wait, we haven't examined the coefficients. We assumed all coefficients were 1. What if we could control the coefficients to improve our approximation? Recall that our goal is to ensure our approximation meets all conditions. That is, at x equals 0, it should match e to the x in the first derivative, second derivative, third derivative, and so on. To address these conditions, let's start with a simple motivation. Assume we have this function. Consider the third derivative of f of x evaluated at x equals 0. The blue terms vanish because they do not survive the third derivative. The red terms also disappear, as although they survive the third derivative, they do not survive evaluation at x equals 0. Therefore, we choose the coefficient arbitrarily. Let's replace 10 with any real number m, so we can write this as. Applying this to the fourth and the fifth derivative, we find Applying this approach to what we have left before, to comply with all the conditions, we get Great, we have a better approximation in the neighborhood of x equals 0. However, we are not finished yet. This approximation only works in the neighborhood of x equals 0, not any real number. What about the neighborhood of x equals 1? For the third derivative of f of x evaluated at x equals 1, the blue terms vanish, but the red terms survive both the third derivative and the evaluation at x equals 1. What shall we do? Now only one term survives. Now we can replace 1 with x0 for x0 being any real number. Therefore we have. Although this is not a proof, I hope that after watching this video we can have a deep understanding of Taylor series, a formula that initially seems very intimidating.